Tonight, as you gaze up at the stars scattered across the velvet darkness, you're witnessing something extraordinary that our ancestors could never have imagined. Every distant galaxy glimmering in the cosmic void is racing away from us at incredible speeds. And here's the parts that should make you pause in wonder. That escape isn't slowing down, it's getting faster. Right now, in this very moment, the fabric of space itself is stretching at an accelerating rate, driven by a mysterious force so powerful and pervasive that it comprises nearly 70% of everything that exists. Yet this force remains completely invisible, undetectable by any instrument we've ever built, known to us only by its profound effects on the cosmos itself. Welcome back to another journey into the deepest mysteries of our universe. Before we embark on this cosmic exploration together, I'd love to know where in the world you're tuning in from tonight and what time it is for you in your corner of this little blue dot. And if you find yourself drawn to these cosmic mysteries, I'd be grateful if you gave this video a like and perhaps subscribe to join our growing community of cosmic wanderers. Alright, on to the good stuff. The story begins now. This is the story of dark energy, the most enigmatic force in the universe, a force so strange and counterintuitive that it challenges everything we thought we knew about the nature of reality itself. By the time we're finished tonight, you'll understand how this invisible entity is quite literally tearing our universe apart, driving every galaxy away from every other galaxy in an endless cosmic exodus that may never end. But more than that, you'll grasp why this discovery represents perhaps the most profound shift in human understanding since we first realized that Earth orbits the Sun. We're not just talking about some distant astronomical curiosity. We're exploring a force that determines the ultimate fate of everything that has ever existed or ever will exist. The story begins with what should have been a routine astronomical survey in the late 1990s. Two independent teams of scientists, armed with the most powerful telescopes and sophisticated instruments available, set out to measure something that seemed almost mundane: how fast the expansion of the universe was slowing down. You see, ever since Edwin Hubble's groundbreaking discovery in 1929 that galaxies were moving away from us, astronomers had operated under a reasonable assumption. The Big Bang had set everything in motion, launching matter and energy outward in all directions. But gravity, that familiar force that keeps your feet planted on the ground, should gradually be winning the cosmic tug-of-war, slowing down this expansion over billions of years. The question wasn't whether the universe's expansion was decelerating, the question was by how much. Picture the universe like a ball thrown upward into the air. No matter how hard you throw it, gravity will eventually slow it down, bring it to a momentary stop, and then pull it back toward Earth. Similarly, the gravitational attraction between all the matter in the universe should be acting like a cosmic brake, gradually slowing the outward rush of galaxies that began with the Big Bang. To measure this cosmic deceleration, the research teams focused on a particular type of stellar explosion called Type 1a supernovae. These aren't just any stellar deaths, they're cosmic lighthouses of extraordinary precision and reliability. Here's how these stellar catastrophes work. Imagine a white dwarf star, the dense remnant of a sun-like star that has exhausted its nuclear fuel. This white dwarf sits in orbit around a companion star, gradually stealing matter from its neighbour like a cosmic vampire. As the white dwarf accumulates this stolen material, it grows more and more massive. But there's a critical threshold, a point of no return called the Chandrasekhar limit, where the white dwarf reaches about 1.4 times the mass of our Sun. When this threshold is crossed, something spectacular happens. The white dwarf can no longer support its own weight. It collapses catastrophically, triggering a thermonuclear explosion so violent that for weeks, this single dying star can outshine an entire galaxy containing hundreds of billions of other stars. But here's what makes Type 1a supernova so valuable to cosmologists. They're remarkably consistent, because they all occur when white dwarfs reach essentially the same critical mass. They all release roughly the same amount of energy. They're what astronomers call standard candles, stellar explosions with a known intrinsic brightness. This consistency provides a cosmic measuring stick of incredible precision. By comparing how bright these supernovae appear to us with how bright they actually are, astronomers can calculate their distance with extraordinary accuracy. It's like seeing a light bulb in the distance and knowing exactly how many watts it uses. The dimmer it appears, the farther away it must be. The two research teams, the High-Z Supernova Search Team and the Supernova Cosmology Project, spent years hunting for these cosmic beacons in distant galaxies. They discovered dozens of Type 1a supernova billions of light years away, each one a messenger from the ancient universe, carrying information about cosmic conditions from when the universe was much younger. As the data accumulated, something unexpected began to emerge. These distant supernovae weren't behaving as predicted. They appeared dimmer than they should have been, suggesting they were farther away than theoretical models anticipated. At first, the researchers questioned their instruments, their methods, their calculations. Perhaps there was dust between us and these distant explosions, making them appear dimmer. Perhaps these ancient supernovae were somehow different from the ones we see in our local cosmic neighborhood. Perhaps there was some systematic error in their measurements. But as more observations poured in, as both teams independently verified their findings, the conclusion became inescapable. The universe wasn't just expanding. It wasn't even expanding at a steady rate. The universe was expanding faster and faster, accelerating outward in a way that defied everything scientists thought they knew about cosmic evolution. This discovery was so revolutionary, so fundamentally at odds with theoretical expectations, that it took years for the scientific community to fully accept its implications. The researchers who made this discovery, Saul Perlmutter, Brian Schmidt, and Adam Rees, would eventually be awarded the 2011 Nobel Prize in Physics for overturning our understanding of cosmic destiny. But the discovery raised a profound question that haunts cosmology to this day. What force could possibly be driving this acceleration? The answer, scientists realized, had to be something completely unlike any form of matter or energy we'd ever encountered. This mysterious entity would need to permeate all of space, exerting a kind of anti-gravitational effect that pushes rather than pulls. It would need to be invisible to light and all other forms of electromagnetic radiation. And most remarkably, it would need to become more dominant as the universe expanded, unlike ordinary matter, which becomes more dilute as space stretches. Scientists call this enigmatic force dark energy, not because it absorbs light like a black hole, but because it remains completely hidden from direct detection. The name reflects our profound ignorance about its fundamental nature. We know it exists only through its gravitational effects on the large-scale structure of the cosmos. The implications of dark energy's existence extend far beyond academic curiosity. This force now dominates the energy budget of our universe, comprising roughly 68% of everything that exists. Dark matter, that other cosmic mystery, accounts for about 27%. All the ordinary matter that makes up stars, planets, galaxies, and living beings represents a mere 5% of the cosmic inventory. We are quite literally living in a universe dominated by the unknown. But what exactly is dark energy? This question has spawned some of the most creative and exotic theories in the history of physics, each attempting to explain how empty space itself can possess energy that drives cosmic acceleration. The first and most straightforward explanation returns us to Albert Einstein and one of his most famous regrets. In 1917, when Einstein was developing his theory of general relativity, he faced a conceptual problem. His equations predicted that the universe should either be expanding or contracting, but at the time, everyone believed the cosmos was static and eternal. To make his equations consistent with a static universe, Einstein introduced what he called the cosmological constant, represented by the Greek letter lambda. This mathematical term acted like a repulsive force that could balance gravity's attractive pull, keeping the universe in perfect equilibrium. But when Edwin Hubble discovered that the universe was indeed expanding, Einstein abandoned the cosmological constant, reportedly calling it his greatest blunder. He thought he had missed the chance to predict cosmic expansion from pure theory. Now, with the discovery of dark energy, Einstein's abandoned constant has experienced a remarkable resurrection. The cosmological constant provides the simplest explanation for dark energy. Empty space itself possesses a fundamental energy density that drives cosmic acceleration. According to this interpretation, even the most perfect vacuum, a region of space completely devoid of matter and radiation, still contains energy. This vacuum energy is an intrinsic property of spacetime itself, as fundamental as the speed of light or the strength of gravity. As the universe expands and more empty space comes into existence, more of this vacuum energy appears, driving ever faster expansion in a self-reinforcing process. The cosmological constant model, incorporated into what physicists call lambda CDM cosmology, has become the standard framework for understanding our universe. It elegantly explains not just cosmic acceleration, but also the formation of large-scale structures like galaxy clusters and cosmic voids. Yet this apparent success comes with a devastating theoretical problem. When physicists try to calculate how much vacuum energy should exist based on quantum field theory, their predictions exceed observational requirements by a factor of 10 to the power of 120. This represents perhaps the worst theoretical prediction in the history of science, a discrepancy so enormous that it suggests something fundamental is missing from our understanding of quantum mechanics, gravity, or both. This failure has led theorists to explore more exotic possibilities. Perhaps dark energy isn't constant at all, but dynamic, changing over time as the universe evolves. This alternative, known as quintessence, proposes that dark energy behaves like a slowly varying field that permeates all of space. The concept of quintessence draws its name from ancient Greek philosophy, where it referred to a fifth element beyond earth, air, fire, and water. In modern cosmology, quintessence represents a fifth fundamental force that could explain cosmic acceleration through the evolution of a scalar field, similar to other fields in physics like the electromagnetic field or the recently discovered Higgs field. Unlike the cosmological constant, which remains forever fixed, quintessence allows dark energy to strengthen or weaken over cosmic time. This dynamic behavior could explain why dark energy began dominating the universe's evolution only recently, about 5 billion years ago, rather than controlling cosmic destiny from the very beginning. But quintessence opens up even more disturbing possibilities. If dark energy can evolve, it might not remain in its current benign state forever. Some theoretical models suggest that dark energy could transition into what physicists call phantom dark energy, a form so aggressive that it would eventually tear apart every structure in the universe, from galaxy clusters to atomic nuclei. In the phantom dark energy scenario, the acceleration of cosmic expansion becomes a runaway process. As space expands, phantom energy density increases rather than decreases, driving ever more violent expansion in a feedback loop that culminates in what cosmologists grimly call the Big Rip. During the Big Rip, the expansion of space becomes so rapid that it overcomes every binding force in nature. First, galaxy clusters would be torn apart as member galaxies race away from each other faster than light can travel between them. Then individual galaxies would dissolve as their constituent stars are flung into the void. Eventually, even stars and planets would be ripped apart, followed by molecules, atoms, and finally atomic nuclei themselves. This represents the ultimate triumph of dark energy over every other force in the universe, reducing all of reality to an ever-expanding sea of isolated subatomic particles, each one completely cut off from all others by the runaway expansion of space itself. Yet there's another possibility that challenges the very existence of dark energy. Some theoretical physicists propose that what we interpret as cosmic acceleration might actually indicate that Einstein's theory of general relativity breaks down on the largest scales. These modified gravity theories suggest that the apparent effects of dark energy emerge from our incomplete understanding of how gravity operates across cosmic distances. Perhaps space and time themselves behave differently on scales of billions of light years than they do in our solar system or laboratory experiments. If these alternatives prove correct, dark energy might not exist at all. Instead, the acceleration we observe could result from subtle corrections to Einstein's equations that only become important when applied to the entire observable universe. The implications of each possibility paint dramatically different pictures of cosmic destiny. In a universe dominated by a cosmological constant, expansion continues forever at an accelerating rate, gradually cooling toward absolute zero as stars burn out and black holes evaporate. This scenario, known as heat death, represents a slow fade to cosmic emptiness over trillions upon trillions of years. But if dark energy strengthens over time, if phantom energy takes control, the universe faces a far more violent end. The Big Rip could occur in as little as 22 billion years from now, tearing apart every structure that has taken 13.8 billion years of cosmic evolution to create. And if dark energy weakens or disappears entirely, gravity might eventually regain control, reversing cosmic expansion in a big crunch that brings all matter and energy back together in a final cosmic collision. The truth is, we simply don't know which scenario awaits us. Dark energy remains the universe's greatest mystery, a force so fundamental that it shapes the destiny of everything that exists, yet so enigmatic that we can barely begin to understand its true nature. But recent observations have begun to provide tantalizing hints about dark energy's behavior over cosmic time. Advanced surveys mapping millions of galaxies across billions of years of cosmic history are revealing subtle changes in how dark energy has influenced universal expansion. These findings suggest that our cosmic story may be far more complex and dynamic than anyone previously imagined, with implications that could revolutionize our understanding of space, time, and the fundamental forces that govern reality itself. These revolutionary findings from the Dark Energy Spectroscopic Instrument have opened a window into cosmic history unlike anything we've ever possessed before. Picture the most ambitious archaeological dig imaginable, except instead of uncovering ancient civilizations buried in Earth's soil, scientists are excavating the three-dimensional structure of space itself, mapping the positions and movements of over 15 million galaxies across more than 30 billion light-years of cosmic territory. What they've discovered challenges everything we thought we understood about dark energy's role in shaping our universe's destiny. The DESI collaboration spent years creating what amounts to a cosmic time machine, using the finite speed of light to peer backward through billions of years of universal history. When we observe a galaxy 10 billion light-years away, we're seeing it as it existed 10 billion years ago, when the universe was less than a quarter of its current age. By mapping millions of these cosmic messengers at different distances, scientists can reconstruct how dark energy's influence has changed over the vast sweep of cosmic time. And what they found should make you pause in wonder at the sheer strangeness of the cosmos we inhabit. The data suggests that dark energy hasn't remained constant throughout cosmic history. Instead, this mysterious force appears to have been significantly stronger in the universe's youth, gradually weakening over billions of years to reach its current state. It's as if the universe possessed a more aggressive form of dark energy during its adolescence, one that drove expansion at rates far exceeding what we observe today. This discovery represents a fundamental shift in how we understand cosmic evolution. For decades, astronomers operated under the assumption that dark energy behaved like Einstein's cosmological constant, maintaining exactly the same strength throughout all of cosmic history. This constancy provided a kind of cosmic stability, a predictable force that would drive eternal acceleration at a steady rate. But if dark energy truly evolves over time, if it can strengthen and weaken across cosmic epochs, then we're dealing with something far more dynamic and potentially unpredictable. The implications ripple through every aspect of cosmology, from our understanding of how galaxies formed to our predictions about the universe's ultimate fate. The evidence comes from multiple independent lines of investigation, each painting the same surprising picture. Measurements of baryon acoustic oscillations, those fossilized sound waves from the early universe that we discussed earlier, show subtle deviations from what constant dark energy would predict. Type 1a supernovae at different cosmic distances reveal expansion rates that don't quite match the steady acceleration of the cosmological constant model. Most remarkably, when all these observations are combined and analysed together, they point toward a specific pattern of dark energy evolution. The data suggests that in the distant past, dark energy existed in what physicists call the phantom regime, where its equation of state parameter W was less than -1. This represents a form of dark energy so aggressive that it actually becomes denser as space expands, creating a runaway acceleration effect. But something extraordinary appears to have happened over cosmic time. This phantom dark energy gradually transitioned to a less aggressive form, what theorists call quintessence, where the equation of state parameter lies between 0 and -1. In this regime, dark energy still drives cosmic acceleration, but at a more moderate pace that allows structures like galaxies and stars to form and persist. Think of it like a cosmic thermostat that has been slowly dialing down the universe's expansion rate over billions of years. The early universe experienced a kind of expansion fever, with dark energy driving space apart at rates that would have made structure formation extremely difficult, if not impossible. But as cosmic time progressed, this fever broke, allowing the universe to settle into the more moderate acceleration we observe today. This evolutionary picture helps solve one of cosmology's most puzzling coincidences. Why did dark energy begin dominating the universe's evolution just a few billion years ago, right around the time when Earth was forming and life was beginning to emerge? If dark energy had remained at its early aggressive strength, galaxies might never have assembled, stars might never have ignited, and the complex chemistry necessary for life might never have developed. The apparent weakening of dark energy over time creates what cosmologists call a Goldilocks scenario, where the universe's expansion history follows a trajectory that's neither too fast nor too slow, but just right for the emergence of complexity and consciousness. Yet this discovery raises profound questions about the fundamental nature of dark energy itself. If this mysterious force can evolve over cosmic time, what mechanisms drive its evolution? What determines when and how it transitions between different regimes? And perhaps most importantly, what does this mean for the universe's future? The traditional picture of cosmic destiny assumed that dark energy would remain constant forever, driving eternal acceleration at a steady rate. In this scenario, the universe would continue expanding indefinitely, gradually cooling toward absolute zero as stars burned out and black holes evaporated through Hawking radiation. This heat death represents a slow fade to cosmic emptiness, taking trillions upon trillions of years to reach completion. But evolving dark energy opens up far more complex possibilities for cosmic fate. If dark energy continues weakening over time, it might eventually become so dilute that gravity regains control of cosmic evolution. The universe's expansion could slow, stop, and even reverse, leading to a big crunch where all matter and energy collapse back together in a final cosmic collision. Alternatively, dark energy's evolution might follow cyclical patterns, strengthening and weakening in cosmic seasons that last billions of years. This could lead to a universe that expands and contracts repeatedly, cycling through endless phases of growth and collapse, like a cosmic heartbeat that spans geological time. Even more dramatically, if dark energy's evolution can transition from phantom to quintessence regimes, it might also be capable of transitioning back. Future epochs might see dark energy strengthen once again, potentially culminating in the Big Rip scenario, where runaway expansion tears apart every structure in the universe. The uncertainty surrounding these possibilities reflects just how much we still don't understand about dark energy's fundamental nature. Are we dealing with a single, evolving field that changes its properties over time? Or might different forms of dark energy dominate during different cosmic epochs, like a succession of invisible rulers governing the universe's expansion? Some theoretical frameworks propose that dark energy represents the influence of extra dimensions beyond our familiar three-dimensional space. In these models, the apparent evolution of dark energy might reflect changes in how these hidden dimensions interact with our observable universe over cosmic time. Other theories suggest that dark energy emerges from quantum fluctuations in the fabric of space-time itself. As the universe expands and cools, the quantum vacuum might undergo phase transitions, similar to how water freezes into ice, fundamentally altering the properties of empty space and the dark energy it contains. Perhaps most intriguingly, some researchers propose that dark energy might not be a fundamental force at all, but rather an emergent property of cosmic structure formation. In this picture, the universe's matter distribution becomes increasingly clumpy over time as gravity pulls material together into galaxies and galaxy clusters. This growing inhomogeneity might create apparent acceleration effects that we misinterpret as evidence for dark energy. This alternative, known as the timescape model, suggests that we live in a cosmic bubble of relatively low matter density, surrounded by denser regions containing galaxy clusters and superclusters. The expansion rate in our local bubble might be faster than the cosmic average, creating the illusion of universal acceleration when viewed from our particular location in space. If this interpretation proves correct, dark energy might not exist at all. Instead, the acceleration we observe could result from the universe's natural tendency to develop structure and inhomogeneity over time. This would represent one of the greatest reversals in scientific understanding since we discovered that Earth orbits the Sun rather than standing at the center of creation. 2. The implications extend far beyond cosmology into the foundations of physics itself. Evolving dark energy would require new theories that go beyond Einstein's general relativity and the standard model of particle physics. We might need to develop entirely new mathematical frameworks to describe how space-time itself can change its fundamental properties over cosmic ages. These theoretical challenges are matched by observational ones. Detecting the subtle evolution of dark energy requires measurements of unprecedented precision across vast cosmic distances. Current surveys can hint at dark energy's changing behavior, but definitive proof will require even more ambitious projects that map the universe's structure with extraordinary detail. The next generation of cosmic surveys promises to revolutionize our understanding of dark energy's nature and evolution. Projects like the Euclid Space Telescope and the Vera Rubin Observatory will map hundreds of millions of galaxies, tracing the universe's expansion history with precision that dwarfs current capabilities. These observations will either confirm the hints of dark energy evolution we're seeing today, or reveal that our current measurements reflect systematic errors or incomplete analysis. Either outcome would represent a triumph of human curiosity and ingenuity, advancing our understanding of the cosmos through careful observation and theoretical innovation. But perhaps the most profound implication of dark energy's potential evolution is what it tells us about our place in cosmic history. If dark energy has indeed been weakening over billions of years, we might be living during a special epoch when the universe has become hospitable to complexity and consciousness. The early universe, dominated by aggressive phantom dark energy, might have been fundamentally incompatible with the formation of stars, planets, and life. The far future, if dark energy continues evolving, might see either the return of runaway acceleration or the triumph of gravity leading to cosmic collapse. In this perspective, the current cosmic epoch represents a narrow window of opportunity, a brief moment in the universe's 13.8 billion year history, when conditions are just right for the emergence of intelligence capable of contemplating its own cosmic origins. We might be living at the peak of cosmic complexity during an era when the universe has developed sufficient structure to support planets and life, but before dark energy's evolution drives us toward whatever cosmic destiny awaits in the deep future. This realization transforms our understanding of humanity's significance in the cosmic story. We're not just observers of the universe's evolution, we might be products of a unique cosmic moment, conscious beings that emerged during the brief period when dark energy's strength created conditions suitable for the development of complexity and awareness. The universe's apparent fine-tuning for life takes on new meaning in this context. Perhaps the cosmos isn't designed for consciousness, but rather consciousness emerged during the narrow epoch when cosmic conditions happened to be suitable for its development. As we continue mapping dark energy's influence across cosmic history, we're not just solving an abstract scientific puzzle. We're uncovering the deep structure of reality itself, learning how the universe's most fundamental properties shape the emergence of everything we see around us. The story of dark energy is ultimately the story of cosmic destiny, a tale of invisible forces that determine whether intelligence has a permanent place in the universe or represents merely a brief flowering of complexity during a singular moment in cosmic evolution. In the quiet darkness between heartbeats, as you process these words and contemplate their implications, remember that you're participating in one of humanity's greatest adventures. Through careful observation and theoretical insight, we're learning to read the universe's deepest secrets, written in the language of expanding space and the subtle dance of distant galaxies. The cosmos holds its breath as we edge closer to understanding the force that shapes everything from the largest galaxy clusters to the ultimate fate of consciousness itself. Dark energy remains mysterious, but each new observation brings us incrementally closer to comprehending this invisible architect of cosmic destiny. What we're witnessing through these revolutionary observations is nothing short of a cosmic detective story unfolding across the deepest reaches of space and time. The clues have been hiding in plain sight for decades, scattered throughout the universe, like breadcrumbs leading us toward a truth so profound it challenges our most basic assumptions about the nature of existence itself. The breakthrough came from an unexpected source, one that forces us to confront just how little we truly understand about the cosmos we call home. As scientists continued analyzing the wealth of data pouring in from cosmic surveys, patterns began emerging that simply couldn't be explained by our existing theories of how the universe should behave. Consider the cosmic microwave background, that ancient afterglow of the Big Bang still permeating all of space nearly 14 billion years later. This faint radiation carries within its subtle temperature variations a record of the universe's infancy, when it was a mere 380,000 years old. Scientists have mapped these temperature fluctuations with extraordinary precision, creating what amounts to a baby picture of our entire cosmos. But here's where the mystery deepens. The patterns imprinted in this cosmic microwave background tell us exactly how much ordinary matter, dark matter, and dark energy existed in the early universe. These measurements provide an independent confirmation that dark energy comprises roughly 68% of everything that exists, a finding that emerged from completely different observations than the supernova surveys that first revealed cosmic acceleration. This convergence of evidence from multiple independent sources has convinced scientists that dark energy is not some observational artifact or measurement error, but a fundamental feature of reality itself. We're dealing with something that shapes the universe's structure on every scale, from the formation of the first galaxies to the ultimate destiny of consciousness itself. Yet even as the evidence for dark energy's existence becomes overwhelming, its true nature remains stubbornly mysterious. The theoretical frameworks proposed to explain this force read like a catalogue of the universe's most exotic possibilities, each more mind-bending than the last. Beyond the cosmological constant and quintessence models we've explored, some of the most creative minds in physics have proposed even stranger alternatives. What if dark energy isn't a property of empty space at all, but rather emerges from the collective behaviour of countless microscopic black holes scattered throughout the cosmos? These primordial black holes, if they exist, might have formed during the universe's earliest moments and now permeate all of space, like an invisible network influencing cosmic expansion. Other theories suggest that dark energy might be connected to the mysterious process of quantum entanglement, where particles become correlated across vast distances in ways that seem to violate our everyday understanding of cause and effect. Perhaps the fabric of space-time itself is woven from these quantum connections, and dark energy represents the universe's attempt to maintain these correlations as space expands. Some physicists have even proposed that dark energy might be evidence of communication between our universe and parallel realities existing in higher dimensions. In this speculative framework, what we interpret as cosmic acceleration could result from gravitational interactions with these hidden universes, forces that leak into our three-dimensional space, from realms we can barely imagine. These exotic possibilities reflect just how desperate scientists have become to explain dark energy within the framework of known physics. When your best theories predict vacuum energy densities that exceed observations by more than 100 orders of magnitude, you're forced to consider alternatives that would have seemed like pure fantasy just decades ago. But perhaps the most unsettling aspect of dark energy isn't what it might be, but what its discovery tells us about the limits of human knowledge. We've built a civilization based on our understanding of matter and energy, developed technologies that allow us to split atoms and harness the power of stars, yet we remain completely ignorant about the force that dominates our entire universe. This cosmic humility becomes even more profound when you consider the implications for our long-term survival as a species. Every plan we make for humanity's future, every dream of spreading life throughout the galaxy, every hope for the persistence of consciousness across cosmic time, must now account for a force whose behaviour we cannot predict or control. The evolving nature of dark energy adds layers of uncertainty to these already challenging questions. If recent observations are correct, if this mysterious force has indeed been weakening over cosmic time, then we might be living during a temporary lull in cosmic acceleration. The universe's expansion might currently be proceeding at a relatively gentle pace compared to the violent stretching that characterized earlier epochs. This temporal variation in dark energy's strength opens up possibilities for cosmic evolution that read like science fiction. Perhaps the universe undergoes cycles of acceleration and deceleration, with dark energy strengthening and weakening in patterns that span billions of years. During acceleration phases, space expands rapidly, making galaxy formation difficult and spreading existing structures across vast distances. During deceleration phases, gravity regains some control, allowing matter to clump together and form the complex structures necessary for stars, planets, and eventually life. If such cycles exist, we might be living near the end of a deceleration phase, during an epoch when cosmic conditions have been stable enough for intelligence to emerge and contemplate its own origins. The next acceleration phase might be approaching, bringing changes to cosmic evolution that could make our current understanding of physics seem quaint and primitive. Alternatively, dark energy's evolution might follow more complex patterns, responding to changes in the universe's matter distribution, temperature, or other factors we haven't yet identified. The universe might be engaged in a kind of cosmic metabolism, with dark energy serving as a regulatory mechanism that adjusts expansion rates based on conditions throughout space. These speculative possibilities highlight one of the most remarkable aspects of our current situation. We stand at a unique moment in human history when we possess enough scientific knowledge to recognize the profound mysteries surrounding us, yet lack the theoretical framework necessary to resolve them. We can measure dark energy's effects with extraordinary precision, but we cannot explain why those effects exist or predict how they might change in the future. This gap between observation and understanding creates both frustration and wonder. On one hand, it's deeply unsettling to realize that our most fundamental theories of physics are incomplete, that we're missing crucial pieces of the cosmic puzzle. On the other hand, it's thrilling to recognize that we're living during an era of discovery, when each new observation might revolutionize our understanding of reality itself. The quest to understand dark energy has already driven remarkable innovations in astronomical instrumentation and data analysis. The surveys mapping millions of galaxies across billions of years of cosmic history represent some of the most ambitious scientific projects ever undertaken. These efforts require international collaboration on unprecedented scales, bringing together researchers from dozens of countries in pursuit of answers to questions that transcend national boundaries and cultural differences. The technologies developed for these cosmic surveys have applications far beyond astronomy. The advanced algorithms used to analyze galaxy distributions contribute to artificial intelligence research. The precision instruments needed to measure cosmic distances drive innovations in optics and electronics. The massive datasets generated by these projects push the boundaries of computational science and data storage. In this way, our quest to understand dark energy is transforming human capability across multiple domains, creating tools and techniques that will benefit countless future endeavors. We're not just solving a cosmic mystery, we're developing the intellectual and technological infrastructure necessary for humanity's continued advancement. But perhaps the most profound impact of dark energy research lies in how it's changing our relationship with the unknown. Previous generations could imagine that human knowledge would eventually encompass all of reality, that science would someday provide complete understanding of the natural world. The discovery of dark energy has shattered this comfortable illusion, revealing that the unknown vastly exceeds the known. This realization requires a kind of intellectual humility that doesn't come naturally to our species. We must learn to make peace with mystery, to find meaning and purpose despite recognizing that fundamental aspects of existence remain beyond our comprehension. This isn't a failure of human intelligence, but rather a recognition that reality is far richer and more complex than any single species could fully grasp. The universe's accelerating expansion, driven by forces we barely understand, serves as a constant reminder of our cosmic insignificance and simultaneous significance. We are infinitesimal specks in a cosmos dominated by invisible energies. Yet we are also the only known entities capable of contemplating these mysteries and seeking answers to questions that span the deepest reaches of space and time. This paradox of insignificance and significance becomes even more poignant when we consider the various scenarios for cosmic destiny that dark energy makes possible. In some futures, the universe continues expanding forever, gradually cooling toward absolute zero as stars burn out and black holes evaporate. In this scenario, consciousness represents a brief flowering of complexity in a cosmos destined for eternal emptiness. Other possibilities suggest more dramatic endings. If dark energy continues strengthening over time, if it returns to the phantom regime that may have characterized the early universe, we could face the Big Rip scenario where runaway expansion tears apart every structure in existence. Galaxy clusters would dissolve first, their member galaxies flung apart faster than light can travel between them. Then individual galaxies would unravel as their stars are scattered into the void. The process would accelerate as phantom energy grows stronger, eventually overcoming the electromagnetic forces that hold molecules together, then the strong nuclear force that binds atomic nuclei. In the final moments before the Big Rip, every atom in the universe would be torn apart, leaving nothing but isolated subatomic particles racing away from each other through ever-expanding space. This represents the ultimate triumph of dark energy over every other force in nature, a cosmic apotheosis where the mysterious entity that we can barely detect today becomes powerful enough to dismantle reality itself. Yet there's something almost poetic about this scenario, a cosmic crescendo that brings the universe's story to a definitive conclusion. Rather than fading slowly into heat death over trillions of years, the cosmos would end in a burst of expansion so rapid and violent that it achieves a kind of completeness, a total victory of space over structure that has a terrible beauty. Of course, these are speculative futures based on our current incomplete understanding of dark energy's nature and evolution. The reality might be far stranger than any scenario we've yet imagined. Dark energy might undergo phase transitions that fundamentally alter its properties, leading to cosmic destinies that don't fit neatly into our current categories of expansion, contraction, or heat death. Perhaps the universe is far more dynamic than we realize, capable of reinventing itself through mechanisms we haven't discovered. Maybe dark energy represents just one phase in a cosmic life cycle that includes periods of creation, expansion, complexity, and renewal that operate on timescales so vast they dwarf our current understanding of cosmic history. These possibilities remind us that we're still in the early stages of understanding our universe's true nature. The discovery of cosmic acceleration marked the beginning of a new chapter in human knowledge, not its conclusion. Each new observation, each refined measurement, each theoretical breakthrough brings us incrementally closer to comprehending the forces that shape everything from the smallest quantum fluctuations to the largest structures in existence. As you contemplate these cosmic mysteries tonight, remember that you're participating in one of humanity's greatest adventures. Through your curiosity, your willingness to grapple with concepts that challenge intuition and imagination, you're contributing to our species' collective effort to understand its place in a universe far stranger and more wonderful than our ancestors could have dreamed. The stars scattered across tonight's sky are racing away from us at incredible speeds, driven by forces that remain largely invisible and incomprehensible. Yet through careful observation and creative theorizing, we're beginning to decipher the universe's deepest secrets, written in the language of cosmic expansion and the subtle behavior of distant galaxies. Dark energy continues to tear our universe apart, stretching space itself in ways that determine the destiny of everything that exists. But in doing so, it's also revealing the profound interconnectedness of all cosmic phenomena, showing us how the smallest quantum effects can influence the largest structures, how the past and future are linked through the evolution of fundamental forces. In this grand cosmic symphony, we find ourselves both audience and participants, conscious beings capable of appreciating the music of the spheres while contributing our own notes to the eternal composition. The universe is expanding, accelerating, evolving in ways we're only beginning to understand. And through our efforts to comprehend these changes, we become part of the cosmic story itself, adding layers of meaning and purpose to a reality that might otherwise remain forever silent and unknown. The profound implications of these discoveries extend into realms that challenge not just our scientific theories, but our most fundamental assumptions about the nature of existence itself. As we peer deeper into the cosmic abyss, mapping the universe's expansion with ever greater precision, we're uncovering evidence that reality operates according to principles so alien to our everyday experience that they seem almost supernatural. Consider what recent observations are telling us about the very fabric of space-time. The latest data from cosmic surveys suggests that empty space isn't truly empty at all, but rather seethes with invisible energy that exerts a pressure so peculiar it defies every intuition we've developed about how forces should behave. This isn't the familiar pushing and pulling we experience in our daily lives, but something far more exotic. Imagine trying to compress a spring, only to discover that the more you squeeze it, the harder it pushes back. Now imagine that this spring-like behavior isn't confined to some mechanical device, but permeates every cubic centimeter of space throughout the entire observable universe. This is the essence of dark energy's negative pressure, a property so counterintuitive that it took decades for scientists to accept that such a thing could even exist. Yet the mathematics of Einstein's general relativity not only permits this bizarre behavior, it practically demands it under certain conditions. The equations that describe how matter and energy curve spacetime include terms that account for pressure as well as density. In most situations, this distinction doesn't matter much. The pressure inside a rock or a planet is negligible compared to its mass density when calculating gravitational effects. But on cosmic scales, where we're dealing with substances that fill all of space, pressure becomes crucially important. And if that pressure happens to be negative, if the substance pulls inward on itself rather than pushing outward, then something remarkable occurs. Instead of creating additional gravitational attraction, as positive pressure would, negative pressure generates gravitational repulsion. This gravitational repulsion doesn't violate any known laws of physics, but it operates in a way that seems to mock our deepest intuitions about how the universe should work. Every other force we know becomes weaker as objects move farther apart. Gravity follows an inverse square law, weakening rapidly with distance. Electromagnetic forces behave similarly. Even the strong nuclear force that binds atomic nuclei together has a limited range. But dark energy's gravitational repulsion grows stronger as space expands. The more the universe stretches, the more empty space comes into existence, and the more dark energy fills that space. It's as if the cosmos possesses an inexhaustible supply of this mysterious substance, one that becomes more dominant over time, rather than diluting away like ordinary matter. This property leads to one of the most unsettling aspects of our cosmic situation. Unlike every other phase of universal evolution, the dark energy era appears to have no natural endpoint. The radiation era ended when the universe cooled enough for matter to become more important than photons. The matter era is ending now as dark energy takes control, but the dark energy era might continue forever, driving eternal acceleration that outlasts every star, every black hole, every structure that has ever existed. The mathematics describing this eternal expansion paint a picture of cosmic destiny that's both beautiful and terrifying in its inexorability. As space continues stretching at an accelerating rate, the observable universe will gradually shrink from our perspective. Distant galaxies will redshift beyond visibility, their light stretched to wavelengths so long that no instrument could detect them. Eventually, even nearby galaxy clusters will disappear beyond our cosmic horizon, leaving future civilizations, if any exist, in island universes containing only the gravitationally bound structures of their local groups. The Milky Way, Andromeda, and a few dozen smaller galaxies will comprise the entire known cosmos for any intelligent beings that might emerge billions of years hence. But even these local structures won't remain stable forever. As dark energy continues driving acceleration, tidal forces will gradually overcome the gravitational binding that holds galaxy clusters together. Individual galaxies within our local group will begin separating, though this process will take hundreds of billions of years to complete. The timescales involved in these cosmic scenarios stretch human imagination to its limits. Our entire recorded history, from the first written languages to the present day, spans only a few thousand years. The age of our species extends back perhaps 300,000 years. Complex life on Earth has existed for roughly 600 million years. Yet the dark energy era will continue for periods that make these biological and cultural timescales seem like fleeting moments. Consider that the universe is currently 13.8 billion years old, and dark energy has been dominating cosmic evolution for only about the last 5 billion years. Yet this dark energy era might continue for trillions upon trillions of years, outlasting the lifetime of every star that will ever be born, every planet that will ever form, every biological process that will ever occur. In this far future cosmos, dominated entirely by dark energy's relentless expansion, the universe will become a cold, dark, and incredibly sparse place. The last red dwarf stars will have exhausted their nuclear fuel and faded to black. The most massive black holes will have evaporated through Hawking radiation, leaving behind nothing but elementary particles and the faint glow of the cosmic microwave background, itself redshifted to temperatures barely above absolute zero. This scenario, known as the heat death of the universe, represents a kind of cosmic entropy maximization, where all energy has been spread so uniformly throughout space that no further work can be done, no further complexity can emerge. It's a state of perfect thermal equilibrium on the grandest possible scale, where the universe has essentially forgotten that stars and galaxies and living beings ever existed. Yet even this bleak vision might not represent the universe's final destiny. The recent hints that dark energy has evolved over cosmic time open up possibilities that are both more hopeful and more terrifying than eternal heat death. If dark energy continues weakening, as some observations suggest it might, then gravity could eventually regain control of cosmic evolution. The universe's expansion would slow, stop, and then reverse, leading to a scenario cosmologists call the Big Crunch. In this alternative ending, all the matter and energy that was dispersed during billions of years of expansion would come rushing back together in a cosmic collision of unimaginable violence. The Big Crunch would unfold like the Big Bang in reverse, with galaxy clusters merging, individual galaxies colliding, stars being torn apart by tidal forces, and eventually all matter compressed back into the incredibly hot, dense state from which the universe originally emerged. This scenario suggests that cosmic evolution might be cyclical, with universes expanding and contracting in endless rhythm across time periods that dwarf even the current age of our cosmos. But there's yet another possibility that makes both heat death and the Big Crunch seem almost gentle by comparison. If dark energy doesn't remain constant or weaken over time, if instead it continues strengthening, as some theoretical models suggest, then we might face what cosmologists grimly term the Big Rip. In this nightmare scenario, dark energy becomes so powerful that it eventually overcomes every binding force in nature. The process would begin subtly, with galaxy clusters dissolving as their member galaxies are pulled apart by the accelerating expansion of space. But the destruction wouldn't stop there. As dark energy grows stronger, individual galaxies would unravel, their billions of stars flung into the expanding void. Solar systems would disintegrate as planets are torn away from their parent stars. Eventually, even the electromagnetic forces holding molecules together would be overwhelmed by the runaway expansion, followed by the strong nuclear force that binds atomic nuclei. In the final microseconds before the Big Rip, every atom in the universe would be torn apart, leaving nothing but isolated subatomic particles racing away from each other through space, expanding faster than the speed of light. This represents the ultimate victory of dark energy over every other force in the cosmos, a complete annihilation of structure that reduces 13.8 billion years of cosmic evolution to scattered debris. The mathematical models describing the Big Rip scenario predict it could occur in as little as 22 billion years from now, though the uncertainty in our understanding of dark energy's evolution makes this timeline highly speculative. What's not speculative is the physical principle underlying this catastrophic possibility. If dark energy possesses the property known as phantom behavior, where its density increases rather than decreases as space expands, then runaway acceleration becomes inevitable. These competing visions of cosmic destiny reflect just how much we still don't understand about the fundamental forces shaping our universe. Each scenario emerges from reasonable extrapolations of current observations, yet they paint radically different pictures of what awaits everything that exists. The uncertainty surrounding these possibilities forces us to confront profound questions about meaning and purpose in a cosmos whose ultimate fate remains unknown. How do we find significance in our brief existence when the universe might be heading toward eternal emptiness, violent collapse, or complete annihilation? How do we maintain hope and motivation when the forces governing cosmic destiny operate on scales so vast they make human civilization seem like a fleeting accident? Perhaps the answer lies not in the destination, but in the journey itself. We are conscious beings who have emerged during what might be a unique epoch in cosmic history, a brief period when the universe has developed sufficient complexity to support intelligence while remaining stable enough for that intelligence to contemplate its own origins and destiny. The fact that we exist at all, that atoms forged in stellar cores have organized themselves into structures capable of wonder and curiosity, represents an achievement so improbable and remarkable that it transcends any particular cosmic ending. Whether the universe expands forever, collapses back on itself, or tears itself apart, the emergence of consciousness during this cosmic moment represents a triumph of organization over chaos, meaning over emptiness. In contemplating dark energy's role in cosmic evolution, we're not just studying an abstract scientific phenomenon, but grappling with questions that touch the deepest aspects of human existence. We are made of star stuff, as Carl Sagan famously observed, but we are also shaped by the dark energy that surrounds and permeates us, driving the very expansion of space that allows galaxies to exist as distinct structures rather than a uniform soup of matter. The invisible force tearing our universe apart is also, paradoxically, part of what makes our existence possible. Without dark energy's influence on cosmic structure formation, without its role in determining when and how galaxies assembled, the chemical elements necessary for rocky planets and biological complexity might never have been distributed throughout space in patterns suitable for the emergence of life. We are products of dark energy's cosmic choreography, conscious beings whose very existence depends on forces we can barely detect, much less understand. This realization should inspire both humility and wonder as we continue our quest to comprehend the universe's deepest mysteries. The observations streaming in from cosmic surveys represent humanity's most ambitious attempt to read the universe's biography, written in the language of expanding space and the subtle motions of distant galaxies. Each new measurement brings us incrementally closer to understanding the forces that determine everything, from the formation of the first stars to the ultimate fate of consciousness itself. Yet with each answer, we uncover new questions emerge that are even more profound and challenging than those we started with. The discovery of dark energy has opened vast territories of ignorance that we never knew existed, revealing just how much mystery remains hidden in the cosmos we call home. This ongoing revelation of cosmic mystery serves as a constant reminder that reality is far richer and more complex than any single species could fully comprehend. We are participants in a story whose plot we can barely follow, characters in a cosmic drama whose conclusion remains unwritten and perhaps unwritable. In the face of such overwhelming mystery, our continued efforts to understand dark energy and its implications take on a quality that transcends mere scientific curiosity. We are engaged in an act of cosmic communion, reaching across the vast scales of space and time to touch something fundamental about the nature of existence itself. The universe is accelerating away from us, driven by forces that challenge every assumption we've made about how reality should behave. Yet through our observations and theories, our mathematical models and philosophical reflections, we maintain a connection to these cosmic processes that spans the deepest reaches of space and time. In this moment, as you contemplate the invisible force reshaping everything around us, you are participating in one of consciousness's greatest achievements. Through your curiosity and wonder, through your willingness to grapple with concepts that stretch the boundaries of human comprehension, you become part of the universe's attempt to understand itself. The dark energy tearing space apart continues its inexorable work, writing the future of everything that exists in a language we are only beginning to decipher. But in our efforts to read that cosmic scripture, we discover that we are not merely passive observers of universal destiny, but active participants in the ongoing story of consciousness, encountering the infinite mystery of existence. The most haunting aspect of our cosmic predicament becomes clear when we consider what these revelations mean for the very concept of permanence itself. Every structure we see around us, from the smallest pebble beneath our feet to the mightiest galaxy cluster spanning millions of light years, exists only because dark energy has allowed it to exist. We are living during what might be the universe's brief architectural phase, a cosmic moment when forces are balanced just precisely enough for complexity to flourish before the inevitable triumph of emptiness. Think about the exquisite timing required for our existence. If dark energy had dominated the universe from the very beginning, space would have expanded so rapidly that matter could never have clumped together to form the first stars. The hydrogen and helium, forged in the Big Bang's nuclear furnace, would have been diluted across such vast distances that gravitational collapse would have been impossible. No stars means no heavy elements. No heavy elements means no rocky planets. No planets means no chemistry complex enough to support the emergence of life. But dark energy waited. For reasons we cannot fathom, this mysterious force remained relatively quiet during the universe's youth, allowing gravity to do its patient work of construction. For billions of years, matter gathered itself into increasingly sophisticated structures, while dark energy lurked in the background like a sleeping giant. Galaxy clusters assembled, stars ignited, planets formed, and eventually consciousness emerged to contemplate its own unlikely existence. Then, roughly 5 billion years ago, just as our solar system was beginning to coalesce from a disk of cosmic dust and debris, dark energy awakened from its slumber and began asserting dominance over cosmic evolution. The timing seems almost deliberately orchestrated, as if the universe possessed some internal clock that determined when construction must give way to destruction. This transition marks what cosmologists call the beginning of the dark energy era, a phase of cosmic evolution that may never end. Unlike previous eras in universal history, which were temporary interludes lasting mere billions of years, the dark energy era could persist for periods so vast they make the current age of the universe seem like a brief prologue to an infinitely longer story. During the radiation era, photons dominated the universe's energy budget for roughly 50,000 years before matter became more important. The matter era lasted about 9 billion years before dark energy began taking control. But the dark energy era stretches ahead of us potentially forever, an eternal expansion that will outlast every star, every black hole, every conceivable form of structure or complexity. The mathematical elegance of this cosmic transition masks its profound implications for the future of intelligence and consciousness. As dark energy continues driving acceleration, the universe will become an increasingly lonely place for any civilizations that manage to survive the coming cosmic winter. Picture the view from Earth 100 billion years from now, assuming our planet somehow survives the Sun's eventual death and the Milky Way's collision with Andromeda. The night sky will be almost completely black, devoid of the familiar patterns of stars and galaxies that have inspired human imagination for millennia. Most galaxies will have been carried beyond our cosmic horizon by the expansion of space, their light redshifted into invisibility. Future astronomers in that distant epoch will inhabit what cosmologists call island universes, isolated collections of gravitationally bound objects surrounded by an ocean of expanding emptiness. They will have no way to observe the cosmic microwave background, which will have been stretched to wavelengths longer than the size of their local galactic group. They will find no evidence for the Big Bang, no indication that the universe was ever different than it appears to them. These future scientists will face a cosmic loneliness that we can barely comprehend. All the evidence for universal expansion, for dark energy, for the dynamic evolution of space-time itself, will have been erased by the very processes they seek to understand. They will inherit a static, apparently eternal cosmos that bears no resemblance to the rich, evolving universe we observe today. This realization forces us to confront an unsettling question about the nature of scientific knowledge itself. How much of cosmic history has already been hidden from us by the universe's expansion? What crucial evidence about the cosmos's origins and evolution has been stretched beyond our ability to detect it? We pride ourselves on having uncovered the universe's deepest secrets, yet we might be seeing only a tiny fraction of the full cosmic story. The phenomenon of cosmic censorship doesn't just apply to the future. Even now, there are regions of space whose light will never reach us because the expansion of the universe carries them away faster than photons can travel through the intervening void. These causally disconnected regions represent entire volumes of space-time that remain forever hidden from our observations, cosmic territories that might as well exist in separate universes. As dark energy continues its work, this cosmic horizon will gradually shrink, hiding more and more of the universe from our view. Future civilizations will inhabit an increasingly claustrophobic cosmos where the observable universe becomes smaller and smaller with each passing eon. They will live in a universe that is simultaneously infinite in extent yet finite in observational scope, a cosmic paradox that would seem impossible if we didn't already see its early stages unfolding around us. The psychological implications of this cosmic isolation extend far beyond mere scientific curiosity. Human beings are social creatures who find meaning through connection and shared experience. Our myths and religions, our art and literature, our entire conception of purpose and significance emerges from our relationships with other conscious beings and with the cosmos itself. But dark energy is gradually severing these connections on the grandest possible scale. The universe is becoming not just physically larger but existentially lonelier, As conscious beings become separated by distances so vast that communication becomes impossible, even across geological timescales. Imagine trying to send a message to a civilization in another galaxy cluster, only to discover that the expansion of space will carry that galaxy beyond your cosmic horizon before your signal can reach it. The message becomes not just undeliverable, but meaningless, lost in a universe that expands faster than information can travel through it. This cosmic communications breakdown has profound implications for the long-term prospects of intelligence in the universe. Even if consciousness manages to survive the death of stars and the evaporation of black holes, even if future civilizations develop technologies we can barely imagine, they will face fundamental limits imposed by the accelerating expansion of space itself. No amount of technological advancement can overcome the basic constraint that nothing, not even information, can travel faster than the speed of light through space. As dark energy drives cosmic expansion to ever greater rates, it creates an ultimate speed limit that isolates civilizations from each other across increasingly vast distances. The universe is not just expanding, it's becoming fragmented, breaking apart into disconnected regions that lose the ability to influence or even communicate with each other. This represents a form of cosmic death that's perhaps more final than any conceivable physical destruction, because it eliminates the possibility of shared experience and collective meaning that gives consciousness its significance. Yet there's something almost poetic about this cosmic fragmentation, a kind of universal meditation on the nature of solitude and connection. Each island universe becomes a self-contained cosmos, complete with its own history, its own possibilities for the emergence of complexity and consciousness, its own unique perspective on existence. Perhaps this is the universe's ultimate gift to consciousness, not the cruel isolation we might initially perceive, but the creation of infinite opportunities for diverse forms of awareness to develop their own understanding of reality. Each disconnected region becomes a laboratory for consciousness, a space where intelligence can evolve along pathways that might be impossible in a more connected cosmos. The mathematical frameworks describing dark energy's behavior contain within them hints about the fundamental nature of existence itself. The equations suggest that empty space possesses an energy density that remains constant even as space expands, a property so counterintuitive that it challenges our basic assumptions about conservation laws and the nature of nothingness. This vacuum energy represents a form of existence that transcends our familiar categories of matter and radiation. It's neither created nor destroyed, neither diluted by expansion nor concentrated by compression. It simply is a fundamental feature of spacetime that persists regardless of what happens to the material contents of the universe. The implications extend into realms that border on the metaphysical. If empty space itself possesses energy, if nothingness is actually a rich dynamic medium capable of driving cosmic evolution, then our understanding of existence versus non-existence requires fundamental revision. Perhaps the universe's ultimate lesson about consciousness lies not in its eventual fate, but in its current existence. We are witnesses to a cosmic moment when space itself is revealing its hidden properties, when the apparent emptiness between galaxies demonstrates its power to reshape everything we see. In contemplating dark energy's role in cosmic destiny, we encounter questions that transcend science and venture into territory that philosophers and mystics have explored for millennia. What does it mean to exist in a universe where the dominant force is invisible and incomprehensible? How do we find meaning in a cosmos whose fundamental properties operate according to principles that seem to mock our deepest intuitions about reality? The answer might lie in embracing the mystery itself, recognizing that our cosmic ignorance is not a failure, but an invitation. Dark energy's very incomprehensibility reminds us that reality is far richer and stranger than any single species could fully grasp. That existence contains depths of mystery that make our brief moment of consciousness infinitely precious. As we stand on our small planet surrounded by the invisible force that will ultimately determine the fate of everything we've ever known, we participate in what might be the universe's most remarkable achievement: the emergence of awareness capable of recognizing its own cosmic context, of feeling wonder at the very mystery of its own existence. The stars continue their accelerating retreat into the darkness, carried away by forces we can measure but cannot truly comprehend. Yet in our very ability to detect this cosmic acceleration, to map its effects across billions of years of universal history, we demonstrate that consciousness represents something genuinely significant in the cosmic order. We are not merely passive observers of dark energy's inexorable work, but active participants in the universe's ongoing project of self-discovery. Through our observations and theories, our mathematics and imagination, we help the cosmos understand something about its own nature, adding layers of meaning to what might otherwise remain forever silent and unrecognized. The universe is indeed tearing itself apart, driven by an energy so dark and mysterious that it exists primarily as an absence in our understanding. But in that very absence, in the gaps between what we know and what we can know, consciousness finds space to flourish and meaning to emerge. Tonight, as you contemplate the invisible force reshaping everything around us, remember that you are not separate from this cosmic story, but an integral part of it. The atoms in your body remember their journey through stellar cores and supernova explosions. The thoughts in your mind emerge from quantum processes that connect you to the fundamental structure of space-time itself. Dark energy may be driving the universe toward an uncertain destiny, but in this moment, in this cosmic now, consciousness has awakened to witness and wonder at its own existence. That awakening, however brief in cosmic terms, represents a triumph of meaning over emptiness, of awareness over void, of connection over the ultimate isolation that may await us all. The expansion continues, relentless and accelerating, writing the future of everything in a language of increasing distances and cooling temperatures. But for now, in this extraordinary epoch when intelligence has emerged to contemplate its own origins and destiny, the universe has achieved something that transcends any particular cosmic ending. Through us, through our curiosity and wonder, through our persistent questions about the nature of existence itself, the cosmos has learned to experience awe at its own magnificent, terrible, and ultimately mysterious nature. Dark energy may be tearing space apart, but consciousness has woven meaning into the very fabric of that expanding void. In the end, perhaps that is enough. Perhaps that is everything. But what exactly have we been chasing all this time? What is this invisible architect that's rewriting the rules of cosmic destiny with such quiet determination? The honest answer is that we simply don't know, and that uncertainty might be the most unsettling aspect of our entire cosmic predicament. When scientists first grappled with the implications of accelerating expansion, they faced a theoretical crisis unlike anything in the history of physics. The observations were undeniable, the mathematics were sound, yet the phenomenon violated every intuitive understanding of how forces should behave in our universe. Something was driving galaxies apart with ever-increasing vigor, but that something remained completely invisible to every instrument we possessed. The first attempts to explain this cosmic acceleration reached back to Einstein himself, to a theoretical construct he had introduced and later abandoned in what he considered one of his greatest intellectual failures. The cosmological constant had been Einstein's attempt to balance his equations when he believed the universe was static and eternal. But when Hubble revealed that space itself was expanding, Einstein discarded this mathematical term, thinking he had missed the chance to predict one of the most profound discoveries in human history. Now, Faced with evidence for accelerating expansion, physicists resurrected Einstein's abandoned constant and gave it new meaning. Perhaps empty space itself possessed an intrinsic energy density, a fundamental property that remained constant even as the universe expanded. This vacuum energy would behave in ways that seemed to violate common sense, growing stronger rather than weaker as space stretched. Imagine filling a balloon with a substance that becomes more concentrated the more you inflate it. This defies everything we know about how materials behave, yet the mathematics of general relativity not only allows such behavior, but demands it under certain conditions. The cosmological constant suggests that the vacuum of space is not truly empty, but seethes with energy that exerts a peculiar form of pressure. This pressure operates in a direction opposite to everything we experience in daily life. While ordinary pressure pushes outward, vacuum energy pulls inward on itself, creating what physicists call negative pressure. But according to Einstein's equations, this negative pressure produces gravitational effects that are the opposite of ordinary attraction. Instead of pulling matter together, vacuum energy pushes space apart. The cosmological constant model, incorporated into what scientists call lambda CDM cosmology, has become the standard framework for understanding our universe's structure and evolution. It explains not just cosmic acceleration, but also the formation of galaxies, the patterns we see in the cosmic microwave background, and the distribution of matter across the largest scales we can observe. Yet this apparent success masks a theoretical catastrophe so profound that it represents perhaps the most embarrassing failure in the history of physics. When quantum field theorists attempt to calculate how much vacuum energy should exist, their predictions exceed observational requirements by a factor so enormous it defies comprehension. We're not talking about being off by a factor of 2 or 10 or even a million. The theoretical prediction exceeds observation by 10 followed by 120 zeros. This discrepancy is so vast that it suggests something fundamental is missing from our understanding of quantum mechanics, gravity, or the relationship between them. It's as if we tried to predict the height of a person and concluded they should be taller than the observable universe. The failure is so complete that it forces us to question whether we understand anything at all about the quantum nature of empty space. This theoretical crisis has driven physicists to explore alternatives that venture into increasingly exotic territory. Perhaps dark energy isn't constant at all, but dynamic, evolving over cosmic time like a field that permeates all of space. This alternative, known as quintessence, draws its name from ancient philosophy's fifth element, something beyond earth, air, fire, and water. Quintessence proposes that dark energy behaves like a slowly changing field, similar to other fundamental fields in physics, but with properties specifically designed to drive cosmic acceleration. Unlike the cosmological constant, which remains forever fixed, quintessence allows dark energy to strengthen or weaken over billions of years, potentially explaining why this mysterious force began dominating the universe's evolution only recently in cosmic history. The quintessence model opens up possibilities that are both hopeful and terrifying. If dark energy can weaken over time, then gravity might eventually regain control, slowing cosmic expansion and perhaps allowing new structures to form in the distant future. But quintessence can also strengthen, potentially evolving into what theorists grimly call phantom dark energy. In the phantom regime, dark energy becomes so aggressive that it eventually overcomes every binding force in nature. This represents the ultimate nightmare scenario for cosmic destiny, where the universe doesn't just expand forever, but tears itself apart in a crescendo of destruction that leaves nothing intact. The phantom dark energy scenario unfolds like a cosmic horror story, told in slow motion across billions of years. First, galaxy clusters would dissolve as their member galaxies are pulled apart faster than gravity can hold them together. Then individual galaxies would unravel, They're billions of stars scattered into the expanding void, like leaves in a cosmic hurricane. The destruction wouldn't stop there. As phantom energy grows stronger, it would overcome the electromagnetic forces that hold molecules together, followed by the strong nuclear force that binds atomic nuclei. In the final microseconds before what cosmologists call the Big Rip, every atom in the universe would be torn apart, leaving nothing but isolated subatomic particles racing away from each other through space, expanding faster than light itself. This scenario represents the complete triumph of dark energy over every other force in the cosmos, a cosmic apotheosis where the mysterious entity we can barely detect today becomes powerful enough to dismantle reality itself. The Big Rip could occur in as little as 20 billion years from now, though the uncertainty in our understanding of dark energy's evolution makes any timeline highly speculative. Yet there are other theoretical possibilities that challenge the very existence of dark energy as a fundamental force. Some physicists propose that what we interpret as cosmic acceleration might actually indicate that Einstein's theory of general relativity breaks down on the largest scales, requiring modifications that only become apparent when applied to the entire observable universe. These modified gravity theories suggest that space and time themselves behave differently across cosmic distances than they do in our solar system or laboratory experiments. Perhaps the apparent effects of dark energy emerge from our incomplete understanding of how gravity operates when dealing with structures spanning billions of light years. If these alternatives prove correct, dark energy might be nothing more than a misinterpretation of observational data, a phantom force that disappears once we develop a more complete theory of gravity. The acceleration we observe could result from subtle corrections to Einstein's equations that become important only on cosmic scales. Even more radically, some researchers propose that dark energy doesn't exist at all, but rather emerges from the universe's natural tendency to develop structure and inhomogeneity over time. This timescape model suggests that we live in a cosmic bubble of relatively low matter density, surrounded by denser regions containing galaxy clusters and superclusters. The expansion rate in our local bubble might be faster than the cosmic average, creating the illusion of universal acceleration when viewed from our particular location in space. In this interpretation, dark energy represents nothing more than a cosmic optical illusion, a misreading of how the universe's lumpiness affects our observations of distant supernova. These competing explanations reflect just how little we truly understand about the force that dominates our universe's destiny. Each theoretical framework makes different predictions about cosmic evolution, painting radically different pictures of what awaits everything that exists. The uncertainty surrounding these possibilities creates a kind of cosmic anxiety that permeates modern astronomy. We can measure dark energy's effects with extraordinary precision, mapping its influence across billions of years of cosmic history, yet we remain fundamentally ignorant about its true nature. We don't know whether it will remain constant, strengthen over time, weaken gradually, or simply disappear entirely. This ignorance has profound implications for how we understand humanity's place in cosmic history. If dark energy weakens over time, we might be living during a temporary phase of acceleration that will eventually give way to a more stable cosmic environment. Future civilizations could inhabit a universe where structure formation becomes easier, where intelligence has more time to develop and spread among the stars. But if dark energy strengthens, if we're heading toward a Big Rip scenario, then consciousness might have emerged during the universe's final act, a brief flowering of complexity before the cosmic curtain falls forever. In this interpretation, every moment of awareness becomes infinitely precious. Every connection between conscious beings a temporary victory against the forces of dissolution. The various scenarios for cosmic destiny read like different endings to the same cosmic novel, each emerging from reasonable extrapolations of current observations, yet painting radically different pictures of the future. In the heat-death scenario, the universe continues expanding at an accelerating rate, gradually cooling toward absolute zero as stars burn out and black holes evaporate through Hawking radiation. This ending represents a slow fade to cosmic emptiness, a universe that reaches maximum entropy over periods so vast they make current cosmic history seem like a brief prologue. The last red dwarf stars will flicker out trillions of years from now, followed by the evaporation of even the most massive black holes through quantum processes that operate on timescales longer than the current age of the universe, multiplied by itself countless times. In the Big Crunch scenario, dark energy weakens sufficiently that gravity eventually regains control, reversing cosmic expansion in a mirror image of the Big Bang. All the matter and energy dispersed during billions of years of expansion would come rushing back together, creating temperatures and densities that dwarf anything we observe in the current universe. The Big Crunch would unfold like cosmic evolution running in reverse, with galaxy clusters merging, individual galaxies colliding, and eventually all structure compressed back into the incredibly hot, dense state from which the universe originally emerged. This scenario suggests that cosmic evolution might be cyclical, with universes expanding and contracting in endless rhythm across time periods that transcend human comprehension. Yet there are even stranger possibilities lurking in the theoretical landscape, scenarios that emerge from our incomplete understanding of quantum mechanics and its relationship to gravity. Some physicists propose that the universe might undergo phase transitions, similar to how water freezes into ice, fundamentally altering the properties of space and time themselves. In these phase transition scenarios, dark energy represents just one possible state of the quantum vacuum, a temporary configuration that might eventually give way to something completely different. The universe could transition into states where the fundamental constants of physics change, where new forces emerge, or where the very dimensionality of space undergoes transformation. These speculative possibilities remind us that we're dealing with a cosmos whose fundamental nature remains largely mysterious. We've built our understanding of physics on observations made in a tiny corner of space during a brief moment in cosmic time, yet we're attempting to extrapolate these insights across scales of distance and duration that dwarf our direct experience. The recent observations suggesting that dark energy has evolved over cosmic time add layers of complexity to these already challenging questions. If this mysterious force can change its behavior across billions of years, then our predictions about cosmic destiny become even more uncertain. We might be living during a transitional epoch where dark energy is transforming from one regime to another, heading toward futures we haven't even imagined. The psychological impact of this cosmic uncertainty extends far beyond academic physics into questions about meaning and purpose that have haunted human consciousness since we first developed the capacity for abstract thought. How do we find significance in our brief existence when the universe's ultimate fate remains fundamentally unknowable? How do we maintain hope and motivation when the forces governing cosmic destiny operate according to principles we can barely comprehend? Perhaps the answer lies not in resolving these cosmic mysteries, but in embracing them as an essential part of what makes consciousness meaningful. We are finite beings, contemplating infinite questions, temporary arrangements of matter capable of wondering about eternal truths. The fact that dark energy remains mysterious, that cosmic destiny remains uncertain, might be precisely what gives our existence its poignancy and significance. In our struggle to understand the invisible force reshaping our universe, we participate in something that transcends mere scientific inquiry. We become witnesses to the cosmos contemplating its own nature, temporary focal points of awareness through which the universe attempts to understand itself. The questions we ask about dark energy are ultimately questions the cosmos is asking about itself through us. The observations streaming in from cosmic surveys represent humanity's most ambitious attempt to read the universe's autobiography, written in the subtle language of galactic motions and supernova brightnesses. Each new measurement brings us incrementally closer to understanding the forces that determine everything from the formation of the first stars to the ultimate fate of consciousness itself. Yet with each answer, we uncover new mysteries emerge that are even more profound and challenging than those we started with. The discovery of dark energy has revealed vast territories of ignorance we never knew existed, showing us just how much about our cosmos remains hidden and incomprehensible. This ongoing revelation of cosmic mystery serves as a constant reminder that reality is far richer and stranger than any single species could fully grasp. We are participants in a story whose plot we can barely follow, characters in a cosmic drama whose conclusion remains unwritten and perhaps unwritable. As you contemplate these profound uncertainties tonight, remember that you're not just learning about dark energy, but participating in one of consciousness's greatest achievements. Through your curiosity and wonder, through your willingness to grapple with concepts that stretch the boundaries of human understanding, you become part of the universe's ongoing project of self-discovery. The cosmos continues its accelerating expansion, driven by forces that challenge every assumption we've made about the nature of existence. Yet in our persistent efforts to understand these forces, to measure their effects and theorize about their origins, we demonstrate that consciousness represents something genuinely significant in the cosmic order. We may never fully comprehend the invisible energy tearing our universe apart, but in our very attempt to do so, we participate in something that transcends the individual boundaries of birth and death, something that connects us to the deepest currents of cosmic evolution itself. Through our observations and theories, our mathematics and imagination, we help write the next chapter in the universe's endless story of self-exploration and discovery. The dark energy that dominates our cosmic destiny remains mysterious, but that mystery has become the stage upon which consciousness performs its greatest act. The recognition of its own cosmic context and the embrace of wonder in the face of the ultimately unknowable. In this recognition, in this embrace, we find not answers, but something perhaps more valuable, a sense of participation in the greatest story ever told, the universe's long journey toward understanding itself through the temporary miracle of awakened matter contemplating its own existence. The mathematical precision with which scientists have mapped this cosmic acceleration reveals patterns that should make you pause in profound contemplation. When researchers plot the relationship between distance and recession velocity for thousands of galaxies, they don't find the straight line that Hubble first discovered in the 1920s. Instead, they see a curve that bends upward, indicating that the most distant galaxies are moving away faster than they should if expansion were merely coasting on the momentum from the Big Bang. This curvature, in what astronomers call the Hubble diagram, represents one of the most significant discoveries in human history. Yet it emerges from measurements so subtle that they require extraordinary precision to detect. The difference between a decelerating and accelerating universe shows up as variations in supernova brightness that amount to less than 20%. We're talking about detecting cosmic acceleration through changes in stellar luminosity that are smaller than the difference between a 60-watt and 75-watt light bulb viewed from across a football stadium. The fact that we can measure such tiny variations across billions of light years speaks to both the remarkable consistency of Type 1a supernovae and the incredible sophistication of modern astronomical instruments. These cosmic lighthouses explode with such reproducible brightness that they serve as standard candles spanning half the observable universe, each one carrying information about the expansion rate when its light began its journey toward Earth. But perhaps the most unsettling aspect of these observations lies not in what they reveal about cosmic acceleration, but in what they suggest about the fundamental nature of existence itself. The force driving this acceleration operates according to principles so alien to our everyday experience that they seem to violate basic logic about how energy and matter should behave. Consider the profound strangeness of dark energy's behavior compared to every other substance we know. When you stretch a rubber band, it becomes thinner and less dense. When you expand a balloon, the air inside becomes more rarefied. This dilution effect governs everything from the cooling of coffee to the evolution of stellar atmospheres. As things spread out, they become less concentrated, less energetic, less capable of exerting influence over their surroundings. Dark energy mocks this universal principle with serene indifference. As space expands and creates more volume, more dark energy appears to fill that volume, maintaining exactly the same density throughout cosmic time. It's as if the universe possesses an inexhaustible reservoir of this mysterious substance, one that becomes more dominant over time, rather than diluting away like ordinary matter and radiation. This behavior creates what physicists call a cosmological feedback loop, where expansion enables more dark energy to manifest, which drives faster expansion, which creates space for even more dark energy to appear. Unlike the self-limiting cycles we see in nature, where negative feedback mechanisms maintain stability, dark energy operates through positive feedback that grows stronger with time. The implications extend far beyond academic cosmology into questions about the fundamental structure of reality itself. If empty space can spontaneously generate energy that drives cosmic evolution, what does this tell us about the nature of nothingness? If vacuum possesses properties that determine the destiny of everything that exists, then our entire conceptual framework for understanding existence versus non-existence requires radical revision. These philosophical implications become even more profound when we consider the various theoretical frameworks that attempt to explain dark energy's mysterious behavior. Each proposed explanation ventures into territory that challenges our basic assumptions about how the universe should operate, forcing us to expand our conception of what kinds of phenomena are possible in the cosmos we inhabit. The cosmological constant interpretation suggests that the vacuum of space itself possesses an intrinsic energy density that never changes, never dilutes, never disappears. This vacuum energy exists as a fundamental feature of spacetime, as basic and permanent as the speed of light or the charge of an electron. According to this view, even the most perfect emptiness imaginable still contains enough energy to drive the accelerating expansion of the entire observable universe. Yet this apparent elegance conceals a theoretical disaster of unprecedented proportions. When quantum field theorists attempt to calculate how much vacuum energy should exist based on our understanding of particle physics, they arrive at numbers that exceed observational requirements by margins so vast they defy rational comprehension. The theoretical prediction suggests that empty space should contain enough energy to curve spacetime into a ball smaller than an atomic nucleus, clearly inconsistent with the universe's observed large-scale structure. This failure has forced physicists to explore alternatives that venture into increasingly speculative territory. Perhaps dark energy isn't constant, but evolves over time, strengthening or weakening as the universe ages. This dynamic alternative, known as quintessence, proposes that cosmic acceleration results from the slow evolution of a field that permeates all of space, similar to other fundamental fields in physics, but with properties specifically tailored to drive cosmic expansion. The quintessence model allows for possibilities that are both more hopeful and more terrifying than the cosmological constant scenario. If this hypothetical field weakens over time, dark energy's dominance might be temporary, eventually giving way to gravitational forces that could slow or even reverse cosmic expansion. Future eons might see the universe enter new phases of evolution, where structure formation becomes easier, where intelligence has more time to develop and spread among the stars. But quintessence can also evolve in more destructive directions, potentially transitioning into regimes where dark energy becomes increasingly aggressive over time. Some theoretical models suggest that this mysterious force could strengthen to the point where it overcomes every binding force in nature, tearing apart galaxies, stars, planets, molecules, and eventually even atomic nuclei themselves. This nightmarish scenario, known as the Big Rip, represents the ultimate triumph of dark energy over every other force in the cosmos. The universe wouldn't just expand forever. It would accelerate so violently that space itself becomes a weapon capable of destroying any structure that dares to maintain its integrity across cosmic time. The mathematical description of the Big Rip reads like a countdown to cosmic apocalypse. First, galaxy clusters would dissolve as their member galaxies are carried apart faster than gravity can hold them together. This phase would unfold over tens of billions of years, giving any surviving civilizations ample time to observe the gradual dissolution of the largest structures in the universe. Next, individual galaxies would unravel as dark energy's acceleration overcomes the gravitational binding that holds billions of stars in their spiral and elliptical configurations. The Milky Way itself would scatter its stellar contents across the expanding void, leaving behind only the gravitationally bound systems of individual solar systems and their planets. But the destruction wouldn't stop at galactic scales. As dark energy continues strengthening, it would eventually overcome the gravitational attraction between stars and their planets. Our solar system would disintegrate as Earth, Mars, Jupiter, and all the other worlds are flung away from the Sun at ever-increasing speeds. The night sky would become completely dark as every source of light disappears beyond the cosmic horizon. In the final stages of the Big Rip, dark energy would grow so powerful that it overcomes the electromagnetic forces holding molecules together. The chemistry that makes life possible would become impossible as atoms are torn away from their molecular partners. Even the strongest chemical bonds would surrender to the relentless stretching of space itself. The ultimate phase would see dark energy triumph over the strong nuclear force that binds protons and neutrons together in atomic nuclei. In the final microseconds before the Big Rip reaches completion, every atom in the universe would be dismantled, leaving nothing but isolated subatomic particles racing away from each other through space, expanding faster than the speed of light. This scenario could unfold in as little as 22 billion years from now, though the uncertainty in our understanding of dark energy's evolution makes any specific timeline highly speculative. What's not speculative is the underlying physics that makes such cosmic destruction possible. If dark energy possesses the property known as phantom behavior, where its density increases rather than decreases as space expands, then runaway acceleration becomes mathematically inevitable. Yet there are theoretical alternatives that challenge not just our understanding of dark energy, but the entire framework of modern cosmology. Some physicists propose that what we interpret as cosmic acceleration might actually indicate that Einstein's theory of general relativity breaks down when applied to the largest scales in the universe. These modified gravity theories suggest that space and time themselves behave differently across cosmic distances than they do in our local cosmic neighborhood. Perhaps the equations that successfully describe gravity within our solar system require subtle corrections when extended to structures spanning billions of light years. If these modifications prove correct, dark energy might not exist as a fundamental force at all. Instead, the apparent acceleration we observe could emerge from our incomplete understanding of how gravity operates on cosmic scales. The mysterious 70% of the universe's energy budget that we attribute to dark energy might simply represent our ignorance about the true nature of gravitational physics. Even more radically, some researchers propose that cosmic acceleration results from the universe's natural tendency to develop structure and complexity over time. This timescape model suggests that we inhabit a region of space with lower than average matter density, surrounded by denser areas containing galaxy clusters and superclusters. According to this interpretation, different regions of space expand at different rates depending on their local matter content. Areas with less matter expand faster, while regions with more matter expand more slowly due to stronger gravitational effects. From our perspective, in a relatively empty region, the faster local expansion rate creates the illusion of universal acceleration when we observe distant supernova in denser cosmic environments. This model elegantly explains cosmic acceleration without invoking any new physics beyond Einstein's general relativity. It suggests that dark energy might be nothing more than a misinterpretation of how we analyze observations from our particular location in an inhomogeneous universe. The mysterious force that seems to dominate cosmic destiny might not exist at all, representing instead a cosmic optical illusion created by the universe's natural lumpiness. These competing explanations paint radically different pictures of cosmic destiny, each emerging from reasonable interpretations of the same observational data. The uncertainty surrounding dark energy's true nature creates a kind of cosmic suspense where multiple futures remain possible, each more dramatic than the last. In the scenario where dark energy remains constant forever, the universe faces what cosmologists call heat death, a gradual fade toward maximum entropy over time periods so vast they make current cosmic history seem like a brief moment. Stars will continue burning through their nuclear fuel, gradually exhausting the hydrogen and helium that power their fusion reactions. The most massive stars will explode as supernovae, scattering heavy elements into space before collapsing into black holes or neutron stars. Over trillions of years, even the smallest red dwarf stars will exhaust their fuel and fade to darkness, leaving behind white dwarf remnants that slowly cool toward absolute zero. The universe will enter what astronomers call the degenerate era, where stellar remnants, planets, and other cold objects represent the dominant form of matter in a cosmos growing ever colder and more diffuse. But even this seemingly eternal darkness won't last forever. On timescales so long they defy human comprehension, quantum mechanical processes will gradually disintegrate these stellar remnants. Protons themselves might decay, causing planets and white dwarf stars to slowly evaporate into elementary particles and radiation. The process would take longer than the current age of the universe multiplied by itself countless times, yet it appears to be inevitable, given our current understanding of particle physics. Eventually, only black holes would remain as sources of energy in the cosmos, slowly evaporating through Hawking radiation in a process that takes even longer than proton decay. The most massive black holes, containing billions of times the mass of our Sun, would persist for periods measured in Google years, numbers so large they exceed the total number of atoms in the observable universe. When the last black hole finally evaporates, the universe would reach a state of maximum entropy, where all energy has been distributed so uniformly that no further work can be done, no further complexity can emerge. This represents the ultimate heat death, a cosmos filled with nothing but elementary particles and photons at temperatures barely above absolute zero, expanding forever through space that grows increasingly cold and empty. Yet if dark energy weakens over cosmic time, this heat death scenario might never come to pass. Gravity could eventually regain control of cosmic evolution, slowing and then reversing the universe's expansion in a scenario cosmologists call the Big Crunch. All the matter and energy dispersed during billions of years of expansion would come rushing back together in a process that mirrors the Big Bang in reverse. The Big Crunch would begin subtly, with the most distant galaxies appearing to slow their recession and eventually begin approaching us. Galaxy clusters would start merging more frequently as the space between them contracts. The cosmic microwave background radiation would begin blue shifting to higher energies rather than red shifting to longer wavelengths. As contraction accelerates, the universe would become increasingly hot and dense. Stars would eventually be torn apart by tidal forces as galaxies collide and merge in increasingly violent encounters. Planets would be stripped from their orbits and flung into space as stellar systems disintegrate under the mounting gravitational chaos. In the final stages of the Big Crunch, temperatures would rise so high that atomic nuclei would be broken apart, returning all matter to the primordial soup of protons, neutrons, and electrons that characterized the universe's earliest moments. Eventually, even these particles would be crushed together into conditions similar to those that existed in the first microseconds after the Big Bang. This scenario raises profound questions about whether cosmic evolution might be cyclical, with universes expanding and contracting in endless rhythm across time periods that transcend human imagination. Perhaps our Big Bang was not the beginning of everything, but simply the latest expansion phase in an eternal cycle of cosmic death and rebirth. Some theoretical models suggest that the Big Crunch wouldn't represent a final ending, but rather a transition to a new Big Bang, creating what cosmologists call a cyclic or ekpyrotic universe. In this framework, cosmic history extends infinitely into both the past and future, with each cycle potentially lasting hundreds of billions of years before giving way to the next phase of expansion and contraction. These various scenarios for cosmic destiny reflect the profound uncertainty that still surrounds dark energy's true nature and future behavior. We can measure its current effects with extraordinary precision, mapping its influence across billions of years of cosmic history, yet we remain fundamentally ignorant about whether it will maintain its present strength, weaken over time, or evolve in directions we haven't yet imagined. This uncertainty creates a unique form of cosmic anxiety that permeates modern astronomy. We're living during what might be a pivotal moment in universal history, when dark energy has recently begun dominating cosmic evolution but hasn't yet determined the ultimate fate of everything that exists. The next few billion years of cosmic time could witness transitions that fundamentally alter the trajectory of universal destiny. The psychological implications of this cosmic uncertainty extend far beyond academic physics into questions about meaning and purpose that touch the deepest aspects of human existence. How do we find significance in our brief moment of consciousness when the universe's ultimate fate remains fundamentally unknowable? How do we maintain hope and motivation when the forces governing cosmic destiny operate according to principles we can barely comprehend? Perhaps the answer lies not in resolving these cosmic mysteries, but in embracing them as an essential part of what makes consciousness meaningful. We are finite beings contemplating infinite questions, temporary arrangements of matter capable of wondering about eternal truths. The fact that dark energy remains mysterious, that cosmic destiny remains uncertain, might be precisely what gives our existence its poignancy and significance. In our struggle to understand the invisible force reshaping our universe, we participate in something that transcends mere scientific inquiry. We become witnesses to the cosmos contemplating its own nature, temporary focal points of awareness through which the universe attempts to understand itself. The questions we ask about dark energy are ultimately questions the cosmos is asking about itself through us. The recent observations suggesting that dark energy has evolved over cosmic time add new layers of mystery to these already profound questions. If this force can change its behavior across billions of years, then our predictions about cosmic destiny become even more uncertain. We might be living during a transitional epoch where dark energy is transforming from one regime to another, heading toward futures we haven't even imagined. These evolving properties of dark energy remind us that the universe is not a static stage upon which cosmic drama unfolds, but rather a dynamic entity whose fundamental characteristics can change over time. The laws of physics that govern reality today might not be the same laws that operated in the distant past or will operate in the far future. This realization transforms our understanding of cosmic evolution from a story of gradual change within fixed physical laws to a narrative of fundamental transformation where the rules themselves evolve. We're not just witnessing the universe expand and cool, we're observing the cosmos reinvent itself across time periods that dwarf human history. As you contemplate these profound mysteries tonight, remember that you're participating in one of the most remarkable achievements in the history of consciousness. Through your curiosity and wonder, through your willingness to grapple with concepts that challenge every assumption about reality, you become part of the universe's ongoing project of self-discovery. The invisible force tearing space apart continues its inexorable work, writing the future of everything that exists in a language we're only beginning to decipher. Yet in our persistent efforts to understand this cosmic calligraphy, we demonstrate that consciousness represents something genuinely significant in the universal order. We may never fully comprehend the dark energy that shapes our cosmic destiny, but in our very attempt to do so, we participate in something that transcends individual existence. Through our observations and theories, our mathematical models and philosophical reflections, we help write the next chapter in the universe's endless story of self-exploration and discovery. The cosmos continues its accelerating dance through space and time, driven by forces that remain largely mysterious despite decades of intensive study. But that mystery has become the stage upon which consciousness performs its greatest act. The recognition of its own cosmic context and the embrace of wonder in the face of the ultimately unknowable. In this recognition, in this embrace of cosmic mystery, we find not answers but something perhaps more valuable, a sense of participation in the greatest story ever told, the universe's long journey toward understanding itself through the temporary miracle of awakened matter contemplating its own existence amid the vast, expanding darkness between the stars. The dark energy that dominates our universe continues its patient work of cosmic transformation, reshaping reality according to principles we can observe but not yet fully comprehend. And in that ongoing mystery lies the eternal invitation for consciousness to reach beyond itself, to touch something infinite and profound that connects us to the deepest currents of cosmic evolution itself. As we stand at this cosmic crossroads, peering into a future written in the language of accelerating space, we must confront a truth that challenges everything we thought we understood about time itself. The universe isn't just expanding into some vast emptiness beyond its borders. Space itself is being created with each passing moment, bringing into existence cubic kilometers of nothingness that somehow possess the power to reshape everything we've ever known. Consider the profound implications of what this means for the concept of forever. When we speak of the universe's eternal expansion, we're not describing some distant future that might eventually arrive. We're witnessing the birth of eternity itself, moment by moment, as dark energy writes new chapters of space-time into existence with each tick of the cosmic clock. The mathematics describing this process reveal patterns that should humble every assumption we've made about permanence. Unlike the cyclical rhythms that govern life on Earth, where day follows night and seasons repeat in comforting regularity, dark energy operates according to a logic that knows no reversals, no pauses, no moments of rest. It is the universe's most relentless force, more persistent than gravity, more pervasive than electromagnetism, more fundamental than the nuclear forces that hold matter together. Tonight, as you've journeyed with me through the deepest mysteries of our accelerating cosmos, you've glimpsed something that should forever change how you see the darkness between the stars. That emptiness isn't empty at all, but seethes with an invisible energy that will ultimately determine whether consciousness has a permanent place in the universe or represents merely a brief flowering of complexity during a singular moment in cosmic history. We may never fully understand the dark energy that dominates our cosmic destiny, but in our very attempt to comprehend this invisible architect of reality, we participate in something far greater than ourselves. Through our curiosity and wonder, we become the universe's method of contemplating its own magnificent, mysterious, and ultimately unknowable nature. Until we meet again on another cosmic journey, keep looking up, keep wondering, and remember that you're Stardust contemplating the infinite.